Spaghetti boys!
For the spaghetti bridge, our group decided to base our design on a truss bridge due to the structural benefits, simplicity of design, and also the ability to alter the truss configurations to make the most structurally capable bridge possible. We also chose to follow the truss bridge design due to previous knowledge about trusses and truss configuration learned throughout the course. As you can see from the diagram, a truss bridge is made out of 4 components: top chord, bottom chord, end posts, and the truss members. The truss members are arranged to make a triangular pattern which purpose are to distribute the load force of the bridge throughout the truss members and away from the top and bottom chords, and then into the bridge supports. This process of load transferring allows the truss bridge to be more structurally capable of supporting larger loads. During construction, we used a production line type process. We did this by assigning each group member a bridge member that needed to be reproduced. This allowed for better time efficiency. We ran into an issue here, with the spaghetti parts being bundled together instead of laying in a flat line. This reduced the surface area and made it more hard to stick. As we were working with spaghetti, it was apparent we were going to have some faults in our bridge. We predicted the faults in our test bridge to be located in the truss members, as they were only 4x1 spaghetti lengths thick. A failure in one of these could lead to a collapse in the entire bridge. We reinforced the top and bottom chords, which should prevent them from collapsing. So let's see how we went.
Spaghetti boys!
To do this, we had to firstly analyse why the bridge failed. The reason being the trusses being too thin to withstand the force. To fix this, instead of the spaghetti figuration being 4x1, we made the truss forward by 2, ultimately doubling the thickness of the truss members. This should add strength to the members. For the final test, we also added in extra truss members called king post trusses. These are vertically running members through the trusses to shorten the distance between each of the trusses. This adds strength to the bridge as the top and bottom chord members, in theory, are now shorter and will be less resistant to failure. As spaghetti is quite strong in tension but weak in compression, this shortening of top and bottom members should help greatly. Construction for the final bridge was the same as the test bridge, prefabricating each part and constructing them afterwards. This allowed for each member to do work at home and limit build time. During construction, all group members ensured to use safety and precaution, as the glue used bonds extremely fast and could be dangerous. Today was the day, the final test, to see if the improvements work. When the bridge started to become under pressure, everything looked okay. We hit around the 3 kilogram mark and there was no showing of damage or failure yet. 3.5 kilograms came and the bridge was still in one piece, meaning the improvements of the thicker trusses and king post had worked. Now to see how far it would go. End result left us with 5 kilos, 1.5 kilos more than before. This was a good improvement for our group. The final bridge broke along the top chord under compression, which is understandable as spaghetti is weak in compression. Overall, our group was satisfied with the results of our spaghetti bridge. Although it may not have been the strongest, it only weighed around 130 grams out of a possible 200, which in respect to how much weight it carried, it performed rather well. This project forced us to problem solve, work as a team and put our engineering skills into application more than ever before. The Spaghetti Bridge project is just a tiny scale of what is to come in our careers as construction managers, but we believe we are preparing well. Thanks for watching.